Okay, this is my last lecture on C up there, and this is not out of the textbook. It's out of a separate set of slides. We don't have a final exam, so I'm not terribly worried, but I would feel remiss or that I didn't do my job if I didn't at least touch on this topic here, right there. So I'm not going to go into it in great detail, but I want to at least make you aware of the subject matter and that there, because this is an important part of C programming when you get into any kind of database that you're dealing with, any type of dealing with complex numbers that there, and that is that C allows us to define our own data types, and they can be mixed right there. And these are called structures. So we can define a structure in C, and a structure is something that we define that is made up of simpler data types. So a structure can have strings in it, it can have integers in it, it can have floating point numbers in it, it can have pretty much anything that there. So we're going to define a structure type here, and I'm just going to keep it relatively simple. And as I said before, this is one of those days that my last lecture, I just kind of, about 45 minutes into it, and said I can't go any further. My head is starting to get light, and so it's one of that there. But we're going to define these. Now, this set of slides, he's using the terminology from a database, which is perfectly fine because that's a simple way that we can get there. But we can get there. Oh, and one other thing I should mention before I go on. As I understand, next week's the last official week of classes, but we didn't start this class until 2 or 3 weeks into the semester. So I'm going to run this class as normal. That there, I understand most of you are here for 8 classes anyway for English, right, or something like that. So you're not going home right after next week. So figure probably an extra week of classes to make up for the missing 2 weeks at the beginning. Is that all right with everyone? Okay. Because I need to, in order to do the final project, I need to get into MATLAB a little bit there. So, and as I recall, most of you petitioned for this course, and it took a while before the university agreed to have me teach this class. It was, matter of fact, it's still not on my timetable. So I don't know what the deal is, but I can't update attendance for this class because it's not on my timetable out there. But that's I don't care about attendance anyway, since there's no final exam to bar you from. So it's okay. Getting back to the subject, we're going to define a structure, and the one that he uses first off here, that there is, we kind of go through here, and this is from another Peterson book. Actually, trying to think which book this is from. Problem Solving and Program Design in C. That there. And it's actually not that there. He put his name on it. It's kind of funny that he stole the slides, and the instructor that I downloaded him from put his name as the instructor, but they're the same slides that the publisher gives out. So that there. So they're the same slides if I went to Addison Wesley and downloaded them. But okay, this is the syntax here, and structures have to be defined normally outside of main, in that global area at the beginning of the program, right, where you do the includes. Because if you're going to use structures throughout your program, the same structures, you want them to be universal. So we start off with the keyword type def. So we're defining the type, and it's a structure, and we list all the various elements of that structure within that there, and then we end it with the struct type keyword again. So as I recall, this worked the last time right there. Yeah, sorry, my hand is not that there. But these are keywords right here. That's a keyword. That's a keyword. Those have to be defined strictly the same as they are right there. We always have an opening and closing brace, so this is considered a block right there. And then we can have as many or as few variables within the structure that we want right there. So here's an example. Here we have, actually this is not a keyword, this is the name of the structure. Name of structure. Right there. So here we've defined, with this right here, a structure called student info. Student info is now a data type. It's not a variable, it's a data type. And this particular student info has a name, which happens to be a char array of 20. We could use the string type if we wanted there as well, but we can, that there. And it also includes a name or an age, which is an integer. So there's two different variables whenever we talk about a student info right there. So here we declare the variable. Now what, notice here, this is where we would normally put int, char, string, long, whatever data type we would normally put. Student info is now a data type. So student one is a variable that contains both their name and their age right there. So Wang is the student's name and he's 18 years old, or she right there. So here we can also include, and this is where it gets very, very complex. We declare a class info, which is a new type, but inside of it, we've got an array of 20 students. So we've got 20 students in a class. Each student in the array has a name and an age. So now I've got a structure for a class, right there, class info, but each class has 20 students right there. So here we've got a case right here where here's how we access it right here. Now, we didn't get into string copy or manipulating strings, but you can't set a string equal to a string. You have to use a function called string copy. So here we're copying into student one, which is our structure. We're copying into the subtype name. Name is an array of characters. And Chow is the student's name in this particular case. And again, this particular author who put these slides together use Chinese names, so that's what we're using right there. So this is how we get the data in other than defining it right there. We print the name right there, student.name. Again, it's a type string, and then the age is right there. So we use the dot operator to talk about variables within the structure. If we're dealing with, right there, component right here, that there, I'm not too worried about this, student name plus age at there. But a copy of the entire structure can be done this way. So we can say student one equals student two, right there, which is kind of interesting because the name, when we do this, is copied without using the string copy right there. But again, this gets a little bit more advanced in terms of programming. It wants to reboot my computer. I'm sorry, that there. We'll do that later. So that there. So again, we're looking at here. Here's another particular one where we're defining a structure. This is the structure of planet type. And notice here that there is kind of a key here that when we define a structure, that there, in this particular case, he uses class info. I like this idea of using the underscore T so that I remember that that's a structure, not a variable name. Right there. So here we're defining a planet. It's got a name. It's got a diameter. It's got the number of moons. It's got the orbit time and the rotation time. So it's got 1, 2, 3, 4, 5 different variables within that structure right there. And that's a planet. Now I can have an array of planets. And each planet in the array has got a name, diameter, number of moons, orbit time, and rotational time right there. So this is an example. And again, this whole lecture is just kind of introduce this whole topic here. Is that there? So print planet is a function call right there where we're going to, right there. So print planet is a function call. It's going to receive the structure planet type, and the name of the variable is PL. Again, it's a little bit complex, and you're probably not going to leave this class with a real understanding unless I made you do a program with it. Right there, and we're running short time. But here, so here we're going to print the name of the planet, and notice again the period right here, PL dot name, because name was defined as one of the variables within a planet type, right there. The diameter is, again, we give it a little period dot diameter. That's how we access the internal variables within the structure, and it goes through and does the rest of that there. So this is a relatively interesting way of introducing a structure. Structures are very powerful if you're dealing with large amounts of data, because if I want to have a class of students, I don't want to have 15 different arrays. I'd rather have a structure of students and all their test scores and their averages, and deal with each student individually right there. So again, you know, result. Also note here that when we're doing our scanf, we still have to put our little ampersand in front when we pass it the diameter, because we're passing it a single variable. And when we do scanf, we want to change that variable within the call. We talked about that last week, that whenever we want to change a variable in a function call, we have to pass its address right there. So when we do scanf and we're reading it individually, right there. Whenever we're reading in individual variables within that structure, we have to pass the address of where that's stored. Because in memory, right here, this is our planet right there. The first 20 characters are for the planet name, right? Then the next one, I can't remember what it was, but we'll say it's diameter right there. This is the diameter right there. And we have to pass the address to scanf to read in the diameter. So right there, this is planet, and this is all stored in one block of memory right there. So so we have to pass the individual address. Yeah, diameter was the first one we read. So diameter, then the number of moons right there. So that's why we have to use the ampersand right there. Now again, here we put in the parentheses right there. So scan planet right there. In the parentheses means the address of right there. So we put these parentheses in. And again, I don't expect you to memorize this, but you've seen it at least one time if and when you ever have to deal with this right there. This is considered a little bit more of an advanced C topic, but it's one of the ones that I use a lot. And one of the most common places we would use is if we wanted to find a type called complex that had a real and an imaginary part, for example, right there. So again, they're showing what I try to show with mine right there. But here's the data. There's Earth, its diameter, number of moons, its orbit time, right there. So orbit takes 1 year. 1 year to orbit the sun, and it takes 24 hours to rotate one time, right there. So this is pointing to that right there. I'm going to skip kind of this particular one right here, but this is just kind of a table that shows the same data as right here. I think this actually is probably a better representation of, here we've got a current planet. This is actually the variable name right there. And this is how things are stored in memory right there. So if we had another planet, we would have different information. If we had an array of planets, then we would have a lot of these right after each other right there. And this is kind of a interesting, I forgot the fact that you need the asterisk there to point to the data. So it's a little, that's where the asterisk is required, because we're seeing the contents of what's pointed to by right there. So this is where C gets very cryptic. I think C is a cryptic language to begin with. And when we start dealing with structures and pointers within structures, things get very, very interesting right there. So, right there. So also, you could lose this right here, and it does work. I've actually used it without the percentage asterisk most of the time, right there. Here we're defining a new type. It's another example right here. Our type is time. Now time is actually a predefined type within their time of day, time t, right there, is a predefined type within the type or the time function right there. So structure variable can use as a return variable right there. And I'm going to, again, this code is somewhat messy, but again, notice that what we've got here is new second is equal to this right here. Time of day dot second is equal to new second percent modulus 60. Here we're adding the number of minutes. Here we're adding the number of hours right there. We're modifying the time of day. Again, time of day is of type there, and this is actually calling a function to create a new right there. And again, this is a messy. I'm going to skip over right here. Here's how we deal with arrays of structures. This is really where I wanted to go into next. We define a structure as a student ID number, their GPA. There's two elements within my structure right there. Right there. So then we declare a student list of 50. This is an array of structures. So here we define our type. Student T is a type. And again, it's just like int or string or char or whatever. Right there, it's a basic type now. Here we've declared an array of 50 students. Each student has got an ID and a GPA right there. We put the element number in our opening and closing brackets. before the dot. Right there. So this is the third student in our list, or actually the fourth student, because the first student is 0. The fourth student in our array, their ID number is 929222023. And they have a GPA of 3. So that's how we deal with an array of structures right there. And this is actually simpler. Skip the, erase from memory that whole time discussion, because this is really about the key thing right there. So again, here's our array of structures right there. Each student's got an ID, they got a GPA. And this is the way that you would look at it in memory right there. So again, we can mix these at any types. Here we got wear wig. Now, this is getting into a subject I'm not sure if I want to get into, but this is a union. And a union means that we can share data between different structures. Unions are very popular in x86 programming because some of the registers are shared right there. An example of that would be, again, this is getting into a subject, but in the old 8086 processor, we had a register called AX, which was a 16-bit register, and then we would have AH and AL, which was the upper and the lower 8 bits of that there. So AH would actually point to part of AX right there. So a union means that we have two different variable names that point to the same place in memory. And that gets very complex. So, and I'm not sure how deep I want to get into. I wanted to cover structures, but unions gets to be a similar topic right there. So again, we've got wear wigs and we've got the color right there, and hair type right there. So right here. So here, if hair.bald, right here, you print wears wig, doesn't wear a wig. The hair color is, and here we're using the hair.h there. And again, he's kind of right there where he gets into this discussion. I think I'm going to skip over that there. The union is getting a little messier right there. So that's really what all I wanted to talk about. Now, before I give up here, let me just jump back to the slides that go to this class. And talk a little bit. Again, this was kind of the last topic on C that there, and this idea of linked lists that there. And what a linked list in binary trees are is that we use pointers. Here we have a structure here, and it's called a node, and it points to the next thing in the list. And what it looks like here, right here, is that here's my number 35, and this is a pointer to the next thing in the list, 75, and a pointer to the next thing in the list right here. And this list here is, we're using pointers here to dynamically allocate memory. We don't know how big our list is. We don't want to tie up all of our memory. So we have this concept of we're pointing to the next item in the list. right there. And this is a linked list right there. And it's used for a number of applications right there. And I just want to introduce the term linked list. We have another term called a binary tree. In a binary tree, we have our data right here. And we have two pointers. One points to this tree here, which then points to two more. And we can have a tree structure that starts off at the top of our tree. And you can see it can get quite messy as we go along here. But a binary tree is a two-way linked list. And there's lots of applications for binary trees, especially if we want to read data in and sort it as we read it in, we add it to the tree in order. So we look at the data, do it go to the left side or the right side. And then when we want to find the data, we can find it very quickly. Again, this is a more complex subject and not really part of this course, but I just want to introduce the term a linked list and a binary tree. This book actually goes through here and goes through and sets up a binary tree right there, and there's lots of text there, but I just want to get, let's see again, this is showing that there, notice here that this particular one has not been initialized yet, so it's null. It doesn't point to anything yet. When I add something to it, then I'm going to make this equal to the address of the next thing on the list. So I can dynamically make my memory larger right there. And this has got the advantages that we don't tie up memory unless we need to right there. There's all kinds of functions for that. Memory allocate, memory free, size of, right there. And this goes into much more detail. I'm not going to go into that right there. This talks about it. If you're interested, you can go through chapter 12 of the textbook. You've got the book there. But it goes through that right there. So a node can contain any data type, including structures. That's a key thing about when we deal with linked lists and binary trees, is that they can contain a structure, not just a single data type. So I can have an entire student's information and then link to two more students. And I can sort this tree by student ID number. That way, if I wanted to find a particular student quickly, I can. And this is very important if you're dealing with large amounts of data. I mean, if you're CIB Bank and you want to find a particular student or a particular customer's account quickly based on their account number, you can go through and search that entire database very, very quickly versus going through each and every customer in the database and try to find their right there. So the linked list is appropriate when the number of data is unpredictable and you want to keep your memory. If you know exactly how many customers you've got, then you just set up an array and then sort the array. Right there. So they can increase it that there. So size of an array, this is the key thing, is that they're dynamic. You don't have to know how big they need to be. And when you delete something, you make the list smaller. You can remove a customer. Arrays can become full. Linked lists never run out of memory until the system runs out of memory. Right there. Obviously, if you don't, that there. So linked lists are normally that there. They could be anywhere. Up there. I'm just jumping through here. And this shows another start pointer, points to the first one right there. And there's some here where we can insert a function called start pointer item into the list. We can delete something, and there's some up there. In insert, we say new pointer is allocate memory, the size of, how big that node is, right there. And node, list node is a structure right here. The list node, in this particular case, it just contains a single letter and a pointer to the next thing in the node. This can be a structure right there within the structure, as we just talked about. As I said, this is where C starts getting into very, very complex code beyond the scope of this course. But I'm just trying to give you a little hint at how much you don't know yet. That's a terrible way to put it, telling you how much you don't know yet. But the key thing is you have to realize after about 10 weeks of C, there's a lot you don't know yet about the language. And you'll hear this terminology from time to time when you talk about a linked list. At least you got kind of a viewpoint of how it is. You don't know how to use it yet. You know, until you actually start writing some programs and using it, you're not going to know how to use it. And I've used a lot of linked lists and binary trees for many applications over the years. So I'm quite familiar with how to use them, and I'm quite familiar with how cryptic it gets. And to be honest, if I had to do it today, I would have to do it with a textbook or an internet example in front of me, because I haven't done it recently enough to remember all the steps that there. But this particular example shows the steps involved in setting up a new right there. And also note that you have to also, this particular one is insert, that we're going to put the, in other words, we have to set the pointer to null right there. And this is kind of insert a new at the beginning of the list, and we can put it at there. In this particular case, they're dealing with the case that the memory's full right there. And I'm going to just jump through this right here. This is all the, as you can see, this is pretty interesting example. I want to jump to the next topic right here. And this kind of goes through that program. Delete, it goes through all the functions. Stacks, I'm not going to talk about stacks right there. I'm going to skip stacks right there. Push stack, pop stack, applications of stacks, queues are right there. Queues are for print spooling. Again, that's right here. Here we're showing we got a pointer to the beginning of the list and a pointer to the end of the list right there. I want to skip queues. I want to jump to binary trees. All right, a tree I talked about a minute ago contains two or more links right there. And here the root points to the top. We have a left tree and a right tree. Children of a node are called siblings right there. And what we've got here is, here we've got a case where we're pointing to the beginning of the queue. Here we've got the left subtree, the right subtree, and then we've got the right subtree also has a left subtree right there. So you can see how complex these can get. And binary trees, the primary purpose for binary trees are for search, because when we do a binary tree, we put the data in order. So everything to the left, notice that A is before B in the alphabet. So if I'm looking for A, I look at the value of B, look at the value of B. Well, if it's not B, check the left tree. That there. If it's greater than B, I check the right tree. So I put A on the left tree, D on the right tree, C is less than D, so it goes on the left tree of D, of C. So if I'm looking for C, I'm going to go through B, D to here. E would be over here. If I'm going to put E in, it'll be here, right here. If I put F in, F is going to go here. Now, depending on what I select as my initial value, my tree can be very lopsided. In this particular case, I started off with B as there, and B is toward the top of the... So everything but A is going to show up on the right side of the tree. Right there. So this tree is not going to be very symmetrical. Right there. Oh, I know who that is. My dentist calling. Say I have an appointment tomorrow. That there. So, but that's what a binary tree looks like, right there. And you can see here's an example of a binary tree. Again, notice that 47 is at the top, 25 is less than 47, so it goes over here on the left tree. 77 is greater than 47, so it goes on the right tree. Here's 65 is less than 77, so it goes to 77 and then to the left tree. So we load the stuff up in order, and then if we're looking for a particular value, we traverse the tree until we reach the data we're looking for, or we reach a null pointer where it should be. That there. And this makes searching. And remember that this can be a structure. It can be an entire customer's file right there. So traverses the order, in order, pre-order, post-order right there. And again, this is an example program. I'm not going to go through it. You can see it gets quite lengthy and quite cryptic right there. So right here, here's how we allocate. We do a tree pointer is equal to null, then we allocate a new node. We set both the right and left pointers to null, and we set the data equal to our data right there. And again, this program is quite large right there. And this goes through all that. And I think I'm going to kind of wrap up my discussion on C with a really complex subject, and one that I'm not expecting you to completely grasp, but it is one of those subjects that comes into doing any kind of large program where you're dealing with memory allocation and dealing with pointers. That there many applications end up having to use this type. That there most of what you're going to be doing where you're just dealing with manipulating numbers as an engineer, you're not going to be dealing with trees. But if you ever get into any operating systems or embedded systems, you may run into this whole concept of a linked list or a tree right there. And it's powerful. Structures you'll use a lot. Structures you use a lot. Structures I don't think are that complex to understand. And you'll see structures also when we get into MATLAB. We'll be using structures. We won't be dealing with any binary trees or linked lists in MATLAB. But I just wanted to throw that terminology out there because you'll see it from time to time right there. And this guy goes through that there. That kind of wraps up that chapter right there. So end of C right there. I think I've given you your final C project. I gave you a C project to do. These topics today are not part of that, although I may change that next term and put structures in the final project just simply to force people to use them. But starting on Wednesday, we will be doing MATLAB. Did I open the MATLAB book up yet to where you can download it? The author's name is Palm. It would be on the VLE website if I posted that there. If not, remind me on Wednesday. I'll give you access to the textbook that I'm using for that there, and I'm using the slides that there. But I think Wednesday we'll meet here, but starting next week we're going to meet upstairs in the computer lab in the 6th floor. MATLAB is not installed on these computers, so I have to reserve the room for up there starting on Monday. MATLAB Wednesday, I'll just kind of go through and introduce MATLAB. I'm gonna bring it up here for a few minutes. I haven't talked that long anyway. After minutes. Now MATLAB. Let me just kind of talk a little bit about MATLAB and what it is first. license number. This is license number free for all, so that means it's probably a pirated version. They've got a legit version up on the sixth floor. Unfortunately, it doesn't. The other thing I should point out is MATLAB is a relatively large program. Right there. Oh, I see it. Right there. But let me close this right over here. But MATLAB allows you to write programs. They're called M files. We'll be doing that right there. What MATLAB does best is it does matrices. So A is equal to 1, 2, semicolon, 3, 4. Right there. And it sets up a 2 by 2 matrix right there. And B is equal to 1, semicolon 2, the vector right there. A times B is a multiplication. B times A. Oh, and that won't work. The inner, yeah, because the dimensions. C is equal to 1, 3, like this right here. C equals 1, 3, right there. So that's a row vector. B is a column vector. C is a row vector. C times A. There's my answer. A times C won't work right there because the dimensions won't. And we'll talk a little bit about matrices first, right there. But we're going to look at MATLAB. That there we'll write some programs in MATLAB. In particular, I'm going to do some DC and AC circuit analysis with MATLAB right there. So we'll be talking about MATLAB starting on Wednesday. Wednesday, I'm just going to kind of introduce MATLAB in a more generic term, and then possibly do a little bit of review of matrices. That there, everyone's had linear algebra or math where you know what a matrix is, right? You know what a matrix is, and the term row vector and column vector. You know what an inverse is of a vector. B A raised to the minus 1. Right there where we can find the inverse of a vector, or we can do I and B A. Right there. That gives me the inverse of a vector right there, or a matrix, so that we can do some things with that there. And we'll talk a little bit about how M files work right there. And then I'll probably even talk a little bit, we'll be talking a little bit about how to plot with MATLAB. It does plots very easily right there. So I will go through an introduction on MATLAB on Wednesday. I've got, I'll probably go through MATLAB not real fast because we've got, I'm going to say 2.5 weeks because I'm figuring I'm probably going to go a week beyond the end of normal classes. Possible, and then give you a little bit of time to finish up the course project right there, which will include a C program and a MATLAB project, part of the project right there. So with that said, I'm going to wrap up here. I'm done with C. No, if you got any questions on C, bring them Wednesday. That there, I will be happy to answer that there. I've given you enough C to be dangerous. That there, in other words, you should be able to write relatively simple programs in C. That there, this course is not designed to make you a industrial strength C programmer. Right there. If you're going to be industrial strength C programming, I would have to spend probably 2 semesters on C and get into full detail on that. We spent about 2/3 of a semester on C, so enough to make you at least familiar with it, and you can write some simple programs. That MATLAB, we're probably going to go into not quite as much detail, but MATLAB's a lot easier to use. Right there. And by the way, MATLAB will run C programs right there. So as I said at the beginning of the class, I was going to keep it to where I got to the point that I was not feeling that they're 45